recordings, again, will be on the class website eventually, and on the YouTube channel as well, eventually. All right. Any questions before I get started? All right, so just going forward, just FYI, if you have any questions and don't feel comfortable, saying them out loud for whatever reason, you can always type them in the chat as a direct message to me and I'll answer them. Or you can email me your questions and we can set up a time to talk. Either way, I'm available. So don't get lost. Don't get left behind. If you are feeling like you're getting left behind or lost, let me know and we'll get after it. All right, we'll figure out how to correct that. I'm encouraged to see that most of you submitted the lab from last week. That's good. Continue doing your work because, again, you can get lost really fast just by not doing work, okay? And the things I give you, I don't think are the most difficult. They might take, an hour or so as we get further into the class, but they benefit you if this is what you want to do, right? If you want to be a programmer, if you want to work in tech, they benefit you to know this stuff. If you don't want to do that, I'm not forcing you to be here, right? I hope nobody is forcing you to be here. I hope you're here because this is what you like to do and this is what you would enjoy doing in the future. So do the work to the best of your ability. If you have questions, I'm here to help. All right. So binary, basically it's ones and zeros. And let's see if I can pull up. So I wish, yeah, this is not the same. All right, so I was looking back at the matrix to see if that was ones and zeros, but they actually use symbols and numbers and all kinds of crazy crap. But binary is ones and zeros. So it's technically, it's called base 2 numeral system. What we typically use is base 10. So we have 10 digits, 0 through 9. And with those 10 digits, we can, do 9,464 if we want to. Well, with binary, we only have ones and zeros to work with. We can still represent 9,646 or whatever, but you could only do it with ones and zeros. So you had to use a lot more of them to get there. In computing, each digit is referred to as a bit. So when you think of a bit, so you're getting 1,000 megabits per second. You're getting 1,000 of these zeros and ones per second. So internet connectivity, whatever it may be, you might see 100 Mbps. That means 100 megabits per second. You're getting 100 of these per second. Or if you're on Wi-Fi and it's, well, actually megabits per second is way more than 100 of these. It's more like 1 million of these a second. But if your Wi-Fi is not very strong, you might be getting somewhere in the neighborhood of 500 kbps, which is 500 kilobits per second, which is, in today's standards, is fairly on the low end, right? And you will see that because web pages will take longer to load, whatever it may be. With cell phones, I think 4G, you get about, I want to say maybe like up to 100 megabits per second. But with 5G, you get about 1 gig per second. And we'll talk about what's the difference between gig, megabit. It's basically you do whatever you have times 1,000. So 1,000 bits is 1 kilobit. 1,000 kilobits is 1 megabit. And 1,000 megabits is 1 gig. And we'll talk about that. But binary is the basis for all modern computers. When we talked last time about transistors on a CPU, they run off of bits. Transistors is either on or off, either 1 or 0. So now what is a byte? So when you hear a megabyte or a gigabyte or a kilobyte, what does that mean? Basically, at its most basic form, a byte is 8 bits. 1, 2, 3, 4, 5, 6, 7, 8 is 1 byte. All right. Now we step a little bit further. Now we have 1 byte. A kilobyte is 1,024 bytes, or 2 to the 10 power. Again, we're talking about base 2. We have bits. Everything is either 1 or 0, so we have 2 to the power of 10 bytes. 1 megabyte is 1,024 kilobytes. 1 gig, 1,024 megs. 1 terabyte is 1,024 gigs. All right. When computers first started, having 500 kilobytes was really good, really good. Now we're talking about gigs. Right? We're talking about 1,024, or a lot of computers these days have 4 gigs of RAM. So they have 4 gigabytes of RAM. And you see, if you break that down, that's a lot of bits that you can store on there. Some computers, for storage, they have terabytes. So 2 terabytes of storage, that's quite a bit of storage. However, as we progress, the things we use require way more memory and storage. For example, I used to play Call of Duty Modern Warfare, right? That game alone was 640 gigs. It was over half a terabyte for one game. So you see, the things we use, we use them, we don't think anything of it. But that one game is half a terabyte. So as we keep going further, we'll just keep increasing the amount of data we need. All right, so data representation. So you may have come across the term a 64-bit system versus a 32-bit system. 32-bit systems are kind of old, and they're older. 64-bit is more what we use today, all right? So the main difference is how much RAM your computer can use, all right? Basically, there are different memory addresses in RAM. You can store data in those different addresses. A 64-bit system allows you to have 2 to the 64 different addresses. A 32-bit allows you to have 2 to the 32 different addresses. But you see, it sounds like we just multiplied by 2. But really, each time you add another one, so a 32-bit versus a 33-bit, 33-bit means that you multiplied everything by 2, right? Because this is base 2. So everything is doubled. You have double the amount. So when we go to 64 bits, you see 32, we had about 4 million addresses. 64-bit, we have about 18 quintillion, which this is quintillion down here. That's significantly more than 4 million. So we can use significantly more than 4 million different addresses. All right, so what does binary look like? Again, it's zeros and ones. If you look here, this is 1 byte. 1 byte, 8 bits. Can't say that enough. 1 byte equals 8 bits. Right? Don't ask me why it's 8, it just is. But 1 byte equals 8 bits. All right? How do we convert from binary to decimal? Decimal is what we use, 0 through 9. So how do we convert this little string right here to a decimal number? So I just wrote it out, bigger text. So basically, in binary, you read from right to left, the right one being the most significant bit, right? So whenever this right one, where's my mouse at? Hold on a second. All right, whenever this right one is a 1, your number will be odd. If this right one is a 0, your final number will be even. And that's because we always start from 2 to the power 0, 2 to the power 1, 2 to the power 2, 3, 4, 5, all the way down. 2 to the power 0 is 1. 2 to the power 1 is 2, so on and so forth, all right? So basically, when you have binary, you just write out 2 to the power of whatever. The first one being 0, the next one being 1, next one being 2, 3, and then you do that equation. So 2 to the power of 0 again is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. The power of 3 is 8. Power of 4 is 16. Power of 5 is 32. 6 is 64. And 7 is 128. All right. So we have this. You basically just write that down, and then you multiply. So 1 times 1 is 1. 1 times 2 is 2. 0 times 4 is 0. 1 times 8 is 8. 0 times 16, 0. 1 times 32, 32. 0 times 64, 0. 0 times 128 is 0. Another way of looking at this is basically, if it's a 1, use it. If it's a 0, don't use it. Okay? So when you do all these multiplications, the next step is just add up what you have at the bottom. So you have the 1, you bring the 1 down, you bring the 2 down, you don't bring this one down, you bring the 8 down, you don't bring this one down, you bring the 32 down, and then you add it all up. So this right here in decimal is 43. Okay?
Excuse me, Mr. Brown.
Mm-hmm.
Did you see the message I sent you inside the Zoom call?
Yeah.
I mean, I could just say it again.
I got you.
Oh, okay, because he kept telling me that he wants you to know so he doesn't get marked absent.
I got you.
Just in case. All right, thank you.
Yeah, I'm sorry. It just where I'm at in my room, it's just disconnected for some reason.
That's that good old Shaw Wi-Fi right there. All right, let's see. And the rest of y'all are absent. All right, again, so basically you take out this whole number, you write it out, then you do 2 to the power of whatever as you go all the way down. So 2 to the power of 0, 2 to the power of 1, the power of 2, power of 3, power of 4, power of 5, power of 6, power of 7. If you are smart enough to do those in your head, 2 to the power of 0, anything to the power of 0 is 1, okay? Anything to the power of 0 is 1, except for 0. I can't remember what that is. I think it's still 1. But for any other number, to the power of 0 is 1, all right? Anything to the power of 1 is itself. 2 squared is 4. 2 cubed is 8. 2 to the power of 4 is 16, yada, yada, yada. You basically just bring those numbers down. If it's a 1, you leave it. If it's a 0, then you add it all up. All right? Make sure you're paying attention because this is what we'll do in the lab and the assignment. All right. Now let's try another example. So let's
Question.
convert this. Go ahead.
Professor.
Mm-hmm.
What was the rule that you said? You said that if it's odd at the end, then.
So if this one is a 1, you know your final number will be odd because a 1. Everything else, when you bring it down, is even. If you look at all these other numbers, they're all even, except for this last one.
Okay.
So that means that if this is a 1, you know your final number is going to be odd. For this number,
it's 0. It's going to be
0,
even.
so our final number is going to be even. All right. Just a FYI, if all of these numbers are 0, your final number is 0. If all of these numbers are 1s, your final number is 255. So that's the range between 0 and 255. You can make any number between that range with a byte of data, 8 bits. Of course, and that makes it easier for us humans. 8 bits, the max is 255. Once I add another bit onto that, so let's say I had 9 bits, the max becomes 511, I believe. If I add another bit, the max becomes 1023. So that's why they kind of chop it off at 8 bits. It makes it a little bit easier for us to do our conversions. So we do 8 bits at a time. So let's do this one. I've written it out. I've written out each one of these, 2 to the power 0, power 1, power 2, 3, 4, 5, and 6, and 7. Again, if it's a 1, you bring it down. If it's a 0, you don't bring it down. So the 1, 128, 64, that's a 0, 16, 0, that's a 4, that's a 2, and then you add it all up. And you see our final number is 216. All right. Y'all see what I did there? Just shake your head or put a thumbs up if you see.
Yes.
All right, since y'all shaking your head, now it's your turn. Try to convert these.
Oh, was that when I added the last one? I got 214. I don't know if I was wrong or not.
214. Let's see. I might be wrong. Let's see. 128 plus 64. What did everybody else get? If I'm wrong, let me know. 128 plus 64, 16 plus 4 plus 2. You're right. 214.
I just wanted to make sure.
Mm-hmm. All right. 214. All right. So now y'all try. And I know I'm not dumb. There are conversion calculators out there on the internet. You could just type it in, call it a day, but why not practice? See if you can do it. I'll give you until 11:25. All right. Everybody good?
Yes.
Yeah.
All right. Let's see what these numbers are. Let's see. So the first one is, what did you get?
Oh, I got 165.
Mm-hmm.
I got 149.
149.
Yeah, I got 149.
Yeah, I got 149 too.
All right, let's see.
Oh, did I mess up then? Dang. Okay.
Yeah, I got 149 as well. Let's do it. Let's see what we got. Actually, let's pull up Word. Yeah. Let's do Excel. All right. All right, so what are those numbers again? 1001011 100101 01. All right. So that's what we got, right? All right, so 128, 64, Lord have mercy. 128, 64, 32, 16, 8, 4, 2, and 1. All right. So basically, again, you just take it, bring it down. If it has a 1, if it has a 0, you forget about it. So 128, you bring that one down, bring down 16, bring down 4, and bring down 1. And so this equals the sum of A3 through H3. 149. All right, that was just a Excel summation equation. Everybody see how that I got that? You good?
Yes.
Yay, nay, all right. All right, let's do the
Yes,
next
sir.
one. So the next one is 1101 and then all zeros. What did you all get?
I got 208.
208.
208.
All right, let's see. And all zeros. All right, so 128, 64, 16. Don't have that one. We don't have that one. 208. Yep. Let me just make that a little bit clearer. 208. All right. Next one. What y'all get?
248.
248.
248.
248. All right, let's see. So 32. 8. Yep. All right, and the very last one. What did y'all get? That one's pretty straightforward.
3.
3. Yep.
Yeah, 3.
All right, cool. Everybody clear on that? We got those. If not, let me know. Again, if you have a question, you can write it to me privately in the chat and only I'll see it, or you can send me an email. We can set up a time. All right, so now that we've learned how to go from binary to decimal, how do we go in the reverse direction? So I've made a little table and it looks like there's a lot going on, but we'll just talk about this. All right, so basically we have all of our numbers, right? 2 to the power 0, power 1, 2, 3, 4, 5, 6, and 7, right? 1, 2, 4, 8, 16, 32, 64, 128. We have that, okay? And so we have 241. Say, for example, that's the number that we have, and we want to convert it to binary. So the first thing you look for is 241 less than or equal to, and that should be actually be greater than or equal to. No, I changed this. Okay, hold on. I changed this the other day, and I guess the update didn't get pushed through. Let me see for a second. Yeah. Okay, so the update didn't get pushed through. Hold on a second. Let me fix this real quick. Yeah. All right. Hold on a second. All right. Okay. So the first thing you do is 241 greater than or equal to 128? That's the first question you ask. If that answer is yes, you put a 1. Then you subtract 128 from 241, and this is your remainder, 113. So now you ask, is 113 greater than or equal to 64? If that answer is yes, you put a 1. You subtract 64 from 113, you have 49, I'm sorry. Next question, is 49 greater than or equal to 32? That answer is yes, you put a 1. Then you subtract 32 from 49. Is 17 greater than or equal to 16? If that answer is yes, you put a 1. Then you subtract 16 from 17. So now we have 1. Is 1 greater than or equal to 8? No. You put a 0. You carry that over. Is 1 greater than or equal to 4? No. You put a 0. Carry it over. Is 1 greater than or equal to 2? No. Put a 0. Carry that over again. Is 1 greater than or equal to 1? Yes. We put a 1. You want me to run through that again? All right, I'll run through it again. So our number we want to get to, our target number is 241. Okay. We write out all of our digits, if you will. So starting from 2 to the power 0 all the way down, like we did before. And then we have 241. The first thing you ask is 241 greater than or equal to 128. If it is, our first number is a 1. If it's not greater than that, which we'll do in the next example, it would be a 0. Then you subtract this 128 from 241, right? So what is our remainder? Our remainder is 113. We ask, is 113 greater than or equal to 64? We put a 1. Then what is our remainder after we take that out? 49. Is 49 greater than or equal to 32? Yes. Pull that over. What's our remainder after we subtract 32 from that? 17. 17 is greater than 16, so that's a yes. What's our remainder? Our remainder is 1, because we took 16 from 17, so our remainder is 1. So we know these ones, these three right here are going to be zeros, because all of those are greater than our last remainder. The only thing we have left is this 1. Does that make sense?
Yes.
Let's try another example, which I have to fix real quick, so give me a second. All right, so now let's say our target number is 74. Okay. Again, the first question we asked is 74 greater than or equal to 128? That's a no. So we pull down a 0. Then we go on to the next one. We didn't subtract anything, so we still have 74. Is 74 greater than or equal to 64? That's a yes. So we pull that down. Now we subtract this 64 from 74. So our remainder is 10. Is 10 greater than or equal to 32? That's a no. Pull this over. Is 10 greater than or equal to 16? No. 0. Pull this over again. Is 10 greater than or equal to 8? Yes. So now we have a 1. We subtract 8 from this 10. We have 2 remainder. Is 2 greater than or equal to 4? That's a no. Pull that over. Is 2 greater than or equal to 2? Yes, it is. That's a 1. We subtract 2 from 2, which leaves us with a 0. And you see that last one would be a 0. Again, like I said, if this was an odd number, you know off rip, this would be a 1. Since this is an even number, we know this last one is going to be a 0. That makes sense?
Yes. So do you know, can you do this in your head?
Can I do this in my head?
Or like, do you know people who can do it in their head? Like
I
off
can
rip?
do it in my head for the most part, because if you know, if the number is greater than 128, you're going to use that first digit. Okay, if the number is greater than 192, you're going to use the first 2 digits. If the number is greater than 100, if the number is greater than 200 and I think 24, you're going to use the first 3 digits. So you kind of have ranges in between those. You know what I'm saying? And when you're doing networking, if any of you all get into networking, you'll do these kind of things. So if you look at your computer, you pull up the command line, which is foreign to a lot of people. This is your command line. If I type in ipconfig all, that tells me all of my networking stuff. All right. And you'll see that my computer's, and we'll talk about this in a second, my computer's IP address is this right here, 192.168.1.144. Each one of these dots is a byte, 8 bits. So 192 in binary, that's 11000000. 168 in binary, that's 101000000, or however many zeros at the end. A 1 is 000001. 144 would be 128 plus 16. So 10010000. So that's how computers communicate in binary when they break it down. And we'll talk about that in a second. We'll get to how networking works. So we're kind of running out of time in this class. So we'll do these and we'll pick up next time. All right. Try to convert these 3 numbers and then we'll pick up the rest next time. 89, 112, and 192. And I'll go over this around 11:45, and we'll end the class after that. Again, if you have any questions, you can ask them in class. You can send them to me in a direct chat message, or you can email me and we'll set up time. Don't be shy.
Can you show the other example again, please? Just a chart.
I certainly can.
Thank you.
The numbers were 89, 112, and 192. So write those numbers down and I'll go back to the chart.
I got it.
All right. I'm gonna go back to the chart. I know this might break your concentration a little bit, but if anybody is interested in networking, you can let me know. I used to be a network coordinator at Forsyth Tech Community College. So I did go through all the networking curriculum with Cisco and I got my CCNA. So if anybody's interested in that, I can definitely help you acquire those certifications. All right, so what y'all get for that first one?
For the first one, I got 01011001.
Mm-hmm.
That's what I got.
Me too.
All right, let's see. All right, 89. So 89, is it greater than or equal to 128? It is not. So we do a 0. Bring over 89. 89 is greater than or equal to 64. So we bring down a 1. We subtract 64 from 89, which gives us 25, I believe. Is 25 greater than or equal to 32? That is not. So we bring over 25. Is 25 greater than or equal to 16? It is. So we bring down a 1. Subtract 16 from 25. That gives us 9. Is 9 greater than or equal to 8? It is. So we bring down a 1. Subtract 8 from 9. Leaves us a 1. So from there, I know we don't need these 3 or those 2, and that'll be a 1. Everybody get that?
Yes.
All right. Anybody clear on that? So 0, 1, 0, 1, 1, 0, 0, and 1. All right. Next one is 112. Hold on, let me type it out. 112. All right, what y'all get?
I got 0, 1, 1, 1, 0, 0, 0, 0.
Like that?
Yeah.
Anybody else get something different?
I
Everybody
got lost on this one.
You got lost in this
So,
one? All right.
yeah.
All right, that's cool. So the first question we asked is 112 greater than or equal to 128? It's not, so we got a 0. Pull over 112. Is 112 greater than or equal to 64? It is. Pull down a 1, subtract 64 from 128, which is 48.
It's 48.
Yeah.
48.
So 48. Is 48 greater than or equal to 32? Yep. So bring down a 1. Subtract 32 from 48. That gives us 16. 16 and 16. Yep. That gives us 0. So since all of these are 0, we're done. Once you get 0 as the remainder, you know the rest of them aren't going to be used. So yeah, this is correct. Everybody see that?
Yes.
All right. Last number is 192. This one is pretty straightforward. 192. I actually said it like 5 minutes ago. All right, what did everybody get?
1, 1, the rest are zeros.
Is that what everybody got? Yeah, going. Some of y'all look half asleep. It is 11:48. Y'all rolled out of bed and went to class. All right, so 192 is greater than 128. So we bring down a 1, subtract 128 from 192. That leaves us 64. 64, 64. Pull down a 1. Then the rest of these would be 0. Yep. You are correct. Everybody see how we got that?
Yes.
Yes, sir.
All right, I'm gonna go down the line and I need affirmation. So Caleb, that makes sense?
Yeah, I'm good.
Ashanti,
Yes.
Benjamin,
Yes, sir.
Caleb, I'm assuming Caleb, you're good. Krishan, I got it right this
Oh,
time.
oh, you called me twice? Oh, I'm good.
Krishan,
Yeah, we good.
all
Yeah, we
right.
good. You said it right this time too.
Yeah. Deshaun,
Yeah, we're good.
you good? Jordan,
Yeah.
Julian,
Yeah, I'm straight.
Mariel,
Yeah, I understand.
and Whitney. Whitney, you're last.
So.
You're so. All
I need
right.
to
Well,
practice.
yeah, it just takes practice, and it'll come a little bit easier. But if you need help, I'm here to help whoever needs help. All right, that'll do it for today. Again, we'll pick this back up on Friday. We'll talk about how the internet works. How is it that you are able to connect to me pretty much real time? As I'm talking, you hear me. It's all through wires, physical cables that are connected somehow and that transmit all of this data all the time, 24/7, across the oceans, across the world. So we'll talk about that next time. And I'll
Wait,
see.
so are we meeting on Friday?
So actually, yeah, Friday is actually a lab. So we won't talk about this next time. We'll have a lab on Friday. But on Friday, for those of you who couldn't meet face to face, you lucked out because we have to go online anyway. So we'll do our lab online on Friday.
All right.
All right. Well, I'll see you on Friday then.
Okay. Bye.
Take it easy.
Thank you.
Mm-hmm. Camera's on or you will be marked absent. All right. Camera's on. I know it's Friday. I know y'all probably tired and ready for the weekend, but let's get through this. All right, so I think this is where we left off, decimal to binary conversion. And we'll get to the lab today. So today is supposed to be the lab day, but we'll get to that in a second. I'll probably go over this slide for about 15 minutes, then we'll get to the lab. All right. All right. All right, so we talked about binary. Binary is base 2, right? So 2 to the whatever power. There's also something called hexadecimal. Hexadecimal just makes it easier as human beings to convert these numbers, right? So whereas binary, we only have 2 options, 0 and 1. Hexadecimal, now we have up to 16. So it's actually base 16. And it ranges from 0 to F, right? 0 obviously being 0, 0, 0, 0. In binary, in decimal, it's also 0. In hex, it's 0. Let me fix that. I don't know why it did that. All right. So you see, and basically 0 is 0, F is 16. Okay. So if you think in binary, to get to 16, you would need 4 ones. Okay. Same thing here. I'm sorry, F is 15. There are 16 numbers total, but you range from 0 to 15, 0 inclusively. That makes 16 different numbers. So all zeros is 0 in decimal. That's what we were doing last time. And also 0 in hexadecimal. All ones, there's 4 ones in binary. That equals 15 in decimal. And then hexadecimal, that equals F. So hexadecimal just makes it easier to convert 4 binary numbers, and it makes it so that as human beings, we can read them a little bit easier. So here's the full table. 4 zeros is obviously 0, 0, 0. 3 zeros and a 1 is 1 when you convert it. We get all the way up to 9. In hexadecimal, you have 0 through 9, just like decimal, except whereas in decimal, we would have gone to 10, 11, 12, 13, 14, and 15. In hexadecimal, we start switching to letters, A, B, C, D, E, and F. So 1001 would be 9 in decimal and 9 in hexadecimal. 1010 is 10, but in hexadecimal we say A. 1011 is 11, in hexadecimal we say B. 1100 is 12, hex we say C, then D, E, and F. All right. So now it just takes 4 bits and converts it into one little character, 0 through F. All right, so now we can represent 100 different, or 100 and however many different bits. We can condense it down by 4, right? 4 bits at a time. So let's use this example, binary to hexadecimal. So you see this long kind of binary string right here? If we separate this out into increments of 4, we can convert each one of these into decimal, then each one of those into hex. And honestly, you could skip the decimal part if you're good enough and just go straight to hex. Or you can look at the table. The table tells you exactly the conversions. Right? Split it out into 4s, do the conversion, then you get down to your hexadecimal. All right, that makes sense? Another example. Again, we have this long binary string. We separate it out into 4s. We do our conversions. Then we have our hex. Okay? So hexadecimal is pretty straightforward. Now let's go the inverse way, hex to binary. Again, you separate them out because each one of these represents 4 bits. You do our decimal conversion, so B is 11, 4 is a 4, E is 14, 7 is 7. Then we do our binary conversion from there. Each one being 4 bits. All right. Any questions about hex, binary, and decimal? All right. Because that's what the lab will be. It will be converting from binary to decimal. Then your homework, your assignment this weekend will be hexadecimal. But if you have this table with hexadecimal, it just makes it a lot easier. Because this is all of the possible values of hex. All right. What you do is you have binary, you split it into 4 increments, and then you do your conversions. 4 increments, do your conversions. The inverse way, you split those up, each one representing 4, do your conversions, and there you go, your binary numbers from there. Okay? It's 11:06. Whoever is not here is now absent. Let's see. Yep. All right. So let's talk about networking for a brief little bit right here. So with networking works, all of our computers and laptops, cell phones, whatever it may be, all these different devices are connected through different connection mediums. For example, Wi-Fi is a connection medium. Ethernet is another connection medium. And just FYI, you'll always have faster speeds, typically, on Ethernet instead of Wi-Fi. Reason being, Wi-Fi, it sends those signals out. Every single computer receives those signals. And it's up to your computer to determine which ones are for it. Whereas with Ethernet, they're kind of directed. They come straight to you. Plus, with Ethernet, you're going at the speed of light, essentially. The speed of light is very, very fast. Whereas with Wi-Fi, you're roughly near the speed of sound, which is a lot slower than the speed of light. Think lightning and thunder. You see lightning before you hear the thunder, even though they are the same entity, if you will, right? The lightning produces the thunder, but the speed of light is faster than the speed of sound. Same thing with computers. On Ethernet, the speed of Ethernet is faster than the speed of Wi-Fi, light versus sound. So with Ethernet, you're traveling, it's really the speed of electricity. right? Because you're doing electrical impulses across Ethernet cables. If you hear something called fiber optic, it's actually using light. It's using light signals as your electrical impulse, if you will, to carry that data. So optical fiber is really traveling at the speed of light. It's faster than Ethernet. All right, there's something called your local area network. Basically, it can be organized however you want to, but for me, for example, I have a router, I have my desktop, I have my phone, I have my laptop, my wife has a computer downstairs, she has a laptop. All of those make up our local area network. And we have IP addresses within that local area network. And typically what you'll see is an IP address that starts with 192.168, yada, yada, yada. If you're on a Windows computer and you pull up your command line, you can type in ipconfig/all, and it will tell you all of your Wi-Fi or all of your Ethernet adapters, your network interface cards. So you see on mine, I have something called VMware. These are virtual network cards because I do virtual machines on my computer, which we'll talk about next week. I have an Ethernet adapter right here. This is, where is it? The IP address is right here. My router's IP address, or the default gateway, is this right here, 192.168.1.1. All right. Now, when you look at an IP address, you see these different numbers, 192, 168, 1, and 1. Each one of those are 8 bits. Okay, each one of them is a byte, so 8 bits. Okay, and the reason I'm explaining this is because on the lab, you'll see IP addresses. And so each one of these represents 8 bits. 192 is 8 bits. 168 is 8 bits. 1 is 8 bits. 1 is 8 bits. You know, so that's the reason I'm explaining that to you. So again, your local area network, I have a printer over here that's connected to the internet or connected to my network. So that's part of my local area network as well. Shaw on campus, the whole campus is considered a local area network. But then as you break it down even further, you have more local area networks. So maybe your dorm room, or if you're at home, your house, right? It starts with a router. And our home routers, if you're at home and you have a router, typically it serves 3 purposes, right? The first one is a router. A router connects different networks. So from your internet service provider, if you have Time Warner, or it's called something else now, I can't think of what it's called. Spectrum. If you have Spectrum or DirecTV, you have AT&T, whatever it may be, a router connects that to your local area network, right? And your internet service provider then connects you out to the full internet. But your home router also serves as a wireless access point because it generates your Wi-Fi. In a large institution like Shaw or a larger campus, you'll have dedicated wireless access points. Your home router typically also serves as a switch. A switch just means that you can connect in Ethernet cables into this device. Again, a larger campus will have a dedicated switch device. Our home routers, they don't require as much computing power as a campus. So usually you can get away with combining all 3 of those functions into one device. All right, so you do have something called a MAC address, which is your hardware address. I talked about that briefly last time. Every network interface card has a MAC address. It's given to it from the factory by the manufacturer. It consists of 48 bits. Those 48 bits are then divided into 6 octets, right? An octet meaning octa is 8, so 8 bits. So each one of those, if we break it down, you usually see a MAC address in hexadecimal format, right? So this is an example right here of a MAC address. You see it's 00, which those are hex digits, each one of those being 4 bits. So total, that would be 8 bits. Then 0A, each one of those being 4 bits, so total, that's 8. This is another 8, this is another 8, this is another 8, this is another 8. Like I said, There are 6 of these, each one being 8 bits, each one considered an octet, or you can say each one being a byte. There's many different terms you can use, but in networking, they refer to them as octets. With storage, you refer to them as bytes, okay? And like I said, you have your IP address. We're using typically IP version 4, which is 32 bits, or 4 octets, or 4 bytes. So you see here, again, this is 8 bits, this is 8 bits, that's 8 bits, and that's 8 bits. So 32 total. With 32 bits, if you do the full math, that gives you roughly 4 billion unique addresses, okay? The issue with that is, the issue with IP version 4 is when they created the internet, they created IP version 4, 4 billion addresses sound like that's gonna be enough. But if you think about it now, there are more than 4 billion people on the planet. The average number of devices per person is like 2.5, if you will. So there are about, what, 7.5 billion people. If each person had about 2.5 devices, I mean, you're talking about at least 15 to 20 billion devices worldwide. And that number is growing exponentially because we have IoT devices, we have smart doorbells, we have smart, I saw smart dog collars, we have smart grills. All of those devices need unique addresses. So we've done some creative solutions and schemes to conserve addresses, something called network address translation. However, even that is becoming exhausted. So now we have something called IP version 6, which has 128 bits. And if you remember before, 128 is some ridiculous number. I thought I had it on here, but it's a ridiculously big number of addresses, and theoretically, we should never run out. The issue is, you know, you have a lot of older devices on the internet that don't support IP version 6. So transitioning from IP version 4 to IP version 6, it may never happen because of how the internet is organized. The internet is just organized into a bunch of connected local area networks. So however you manage that local area network is up to you. So Google, for example, has its own standards for managing its network. Shaw has its own standards. All of these connect, and you know, depending on whoever manages those standards, you can have different standards in each location. Okay. So that's why I explained all that IP addressing, networking, because of the lab, and because it's good to have a basic knowledge of networking.